Still, this means that this is the integration over 0 to e of this.
Victor, there is minus sign there, so it will be minus plus.
Where is the minus?
Second term, partial b.
No, partial. We take the partial from the upper limit, so b prime means that partial derivative of e is minus the lower one. Lower one is 0 because integral is started from 0 to 0 to e, so you don't have this that terms. So this is again a surface term. So we can add that 0. There are many ways to forget about that. So we will have just this delta ij integrale how I can insert this when h is between 0 to e. So it was another way, when you have the surface term, when you are passing to the surface, instead of the h you can put an h minus e. In case e is a constant, this is not about this integral. I am talking about this, about the integral in the surface. When you pass from the volume to the area, means that from here, from the volume you pass to the boundary. So boundary is the surface. So on the surface, h is equal to e. So if you have something like partial derivative of this, I don't know, respect to xi, you can replace that by this. Because still you know that the e is a number just.
But in the beginning we say that h equal to e.
Yes, h is equal to e. Yes, but on the surface, just on the surface in the space, only on the surface. But surface means that the surface. But we are trying to find the volume. So, and by this Taylor series, we pass the volume from the volume actually to the area. Taking the derivative of this, I mean partial derivative, this is actually reduced your problem from the volume to the area. Yes, you remember several times I used this. So just if I replace it instead of the h minus e here, so partial derivative of this will be minus 1. So 1 minus y is minus, which we cancel each other. And we are very tricky. So actually the delta E, because still this volume is changing. So I mean this is remain here. So that we can write it omega 0. And we have one delta ij here. Delta ij partial derivative of omega 0 multiplied to delta over omega 0. Something like e. Delta ij partial derivative of logarithm omega 0. Omega over omega 0. this is the volume, sorry, this is the volume of total volume over omega c, and you have one delta. This is actually the omega, so it will be delta ij proportional to logarithm partial derivative of the E logarithm ln omega. Ln omega is the entropy, so delta ij partial derivative of the S over, if you multiply just the car to here, S over E. You need a one car here, so car like that. And if you use the thermodynamic, partial derivative of the S with respect to E is T or 1 over T. I needed to look at the papers. So the last step, I need to check the papers. So
Doctor, why did IDE return back?
yeah. Okay, so yeah, I want to explain that because we lost one part of our discussion. So yes, what did?
Could also the integral for dq dv.
No, there's nothing wrong here, but I needed to write in the better form. So I will tell you that this is one of the rare cases. I needed to be very careful when I write something. So just back a little bit back. That's almost finished, but I want to just to back one step left. You remember that we reduced to that, dq dp. That was the one. You know, the expectation value was integral of xi partial xj. Yes, dq dp over integral dq dp. But as I explained it several times, so this integral is between 0 to e. So we used the Taylor series, but we use it for that. We didn't use for that. We used the Taylor series for both of them because both of them are the real one. The real each one is between these limits. For each of them. For each of them. For each one, you can write the Taylor series, as you know. HQ1 pair between 0 to e, xi, partial xj, d omega, and delta partial e, d omega. I mean dq dp. dq dp. dq dp. Yes, and the HQP. And all the steps remain the same, like, and delta will be cancelled. So we will continue like what we continued that before. So the better way was that you write this expression like this. I try to do not use this. It seems that it's difficult to escape from this condition. What I did it is just I used the fact that energy is a constant, so can I put it instead of the h, I will put h minus e. Energy is a constant. It seems that nothing will be changed because this is a derivative with respect to coordinate. So, and QE is just a number, so taking the derivative from the number, nothing will change.
Doctor, but before we said that the derivative of x
H minus E isn't
No,
minus
don't mix the other discussion with that. I'm talking that E is a constant just. Can you put an E with H? I mean H minus E, the derivative is equal to the derivative of H. Because this is a number just. There is no Q on P here. What you are talking is the difference. H is a function of QP, it still is a function of QP. We didn't make anything to the H. We just added the E here. E is a number, just I added that. So if you start the discussion, so all the proof will be killed actually. So that we don't do something for that. This is, what is that? This is the volume of the phase space. How you want to write it, omega 0 anything. And that we use exactly again the Gauss theorem, like what you reduced it before. As I mean, I write it that like xjf x I h with this. I was looking for that one alternative proof actually, and this proof, just the usual, I told you just make it this total derivative. And again use the concept of the divergence. So this is a divergence of the F over the volume. So can be written as the F dot n of the one lower dimension. If this is over the volume, so this will be over the surface. And the good thing is that when this integral reduced to the surface, and the surface H is equal to E, so that you can put this on the surface. Surface means, I think you not feel comfortable about, this is the phase portrait, so all the problem is to count the volume, and this is the volume, okay? These volumes are made by some surface concentric axis, surface, eccentric surface. For each one, you have this equation for each surface. This is the meaning of equilibrium. Equilibrium means that you have a system in each part, the Hamiltonian should remain the constant. So this integral is over the volume, but now by Gauss theorem, you pass to the area, to the surface. So you are passing to this. When you pass into this, H is equal to E. Not here. You cannot set here H equal to Z. You cannot do here H equal to E. This is the integral over the volume. Over the volume, you don't know what is the H. H is a function of Q and P. But when you pass to the area, like here, and the area H is equal to E. This is the concept of the Gauss theorem. So, very quickly we remove that, and now we are like here, but I want to again write one more time this. Again, exactly, I will repeat this. No harm to repeat something several times, just I don't want you have something with the ambiguity in your notes. So we are here now. So we forget about that. So we have now minus integral partial xi xj delta delta is removed for both. Over yes, partial here. Okay, I use the Leibniz rule again. I use the Leibniz. So using the Leibniz, you see that under this, please keep this minus here. I don't want to mix it this minus with the other one. So if you use the Leibniz, the limit of integral is 0 to E. So like this gives you partial, and this is, you know, we're talking about the delta ij. Can I write it that here also outside? Oh, no, keep it, and later we'll do outside. So it will be delta ij 0 to e partial e h minus e d omega, yes, plus delta ij partial e with respect to e multiplied to h minus e, but over the surface, because remember the light principle. That was the idea why it will be 0. One is that, one of the other is that you think about the loop. So in the loop, the lower and upper limit of integral constant. So the integral will be 0. But I think that was difficult for you to understand. Maybe this is more clear. I don't know. Up to you. So what is that? That is minus 1. This is a partial derivative with respect to e, not with respect to any other things. So 1 minus here, delta ij. So you have delta ij, integral is 0 to e d omega, partial derivative, and integral is 0 to e d omega. Yes? That will be delta ij 1 over partial e logarithm integralities. And this is the total volume. Huh? What is the total volume? Is omega. Delta ij partial ln omega ln e. From the thermodynamic, you know that partial derivative of this is 1 over kBt from different ways. So this it seems that very easy proof, but not very. I'm not happy also about this proof.
Why?
Because it is only for microcanonical. Because we take the rho constant, huh? We take a rho constant and we drop this important term, and this is what in many textbooks they write. You know, the proof is only, they say the proof is general, but it's easy to do for the macrocanonical. So I'm curious to know that how we can do, and for canonical also we can do that. I told you, but I want for very general form. So I want for very general form. So I want we can prove this theorem for the case that rho is rho and only just satisfy the Liouville theorem, Liouville equation. And started from that. So that will be a good project for somebody want to do. But as far as no, it's not done before. It's completely new. To develop a proof for the equipartition theorem for the general and sound. Even not stationary. I will tell you what's my idea. So, and the proof finished. So that will just to explain that the proof. Expectation value of that, we find that this is a KBT delta H. Okay, the case, for example, is interesting is that if you have a Hamiltonian is a function of a QI and PI, or Q and P. For example, QI partial QJ, when both are the same. Also when they are same. Pair, as long as both of them are Q or pair, you can write it even 1 here. So Q partial on the Q or pair partial H pair will be KBT. Yes? The easy example is harmonic oscillator, for example. Look. one-dimensional harmonic oscillator. This is one-dimensional harmonic oscillator. So,
Doctor,
yes.
Doctor, can xi and xj be in the same coordinate?
Of course, they can be same and they can be also different.
Because you said if xi is q, xj